In this video we're going to look at the language and the graphs that we can use to describe motion. So a hopper bus, in our first example, collects customers from hotels and takes them to the airport terminal. The bus starts at Hotel A and then collects passengers from hotels B and C before driving to the terminal. The diagram illustrates the bus's journey from A to the terminal, with the x-axis representing time and the y-axis representing the distance travelled from Hotel A. Now what I'm going to ask you to do when you've seen the whole graph is to just think about a description of the journey. And it's so what I'm going to ask you to do once you've seen the little animation here is to produce a explanation or verbal description of the bus's journey from Hotel A to the terminal. And it's worth recalling that the gradient of a distance time graph, which is what we've got here, gives us the speed. So pause the video at this point and use the distance time graph to describe the journey of the hopper bus from the hotel to the terminal. Distance travelled is a scalar quantity. It has size but no direction. Similarly, speed is also a scalar quantity. It has size but no direction. On the other hand, displacement is a vector quantity which has both size and direction. Now we can represent a vector quantity either as a magnitude and direction or as a column vector. So displacement can be described either as a magnitude and a direction or as a column vector. Velocity of a moving object is also a vector quantity, and it tells us how quickly the displacement of the object is changing. When the motion is along a straight line, the displacement and velocity can be expressed simply by using positive and negative numbers. So a positive displacement means we are moving out in the positive direction along the line, whereas a negative number represents a movement in the negative direction along the line. So let's consider, for example, a daily exercise regime which consists of jogging along a 300-metre stretch of pavement immediately outside Sam's house. If the pavement extends from 100 metres to the left of the front door of Sam's house to 200 metres to the right of the front door, then we could represent the pavement by the portion of the number line running from -100 to 200. And then, if her exercise programme consists of turning right when leaving the house and jogging up and down this stretch of pavement for 4 metres at a constant speed of 5 metres per second, and we'll let t denote the time in seconds that Sam has been jogging, then we can produce a small animation of Sam's run, which shows that during the first 40 odd seconds she's moving to the right, then for the next 60 odd seconds she's moving to the left, next 60 odd seconds she's moving to the right, the next 60 odd seconds she's moving back to the left, and then she ends up back at the home after 240 seconds. Now I'd like you just to pause the video at this stage and think about what modelling assumptions have been made in making the animation of Sam's exercise regime. We can draw 4 different graphs to illustrate these runs. The first one is a simple distance time graph, which will simply show that Sam is covering 5 meters every second. And that, of course, is the gradient of that line. The displacement time graph for Sam's run will show that she starts off by running to the right from the door for the first 200 meters, then switches direction until she's 100 meters to the left of the door, then switches direction again and runs from 100 meters left of the door through to 200 meters to the right of the door, switches direction back to the left hand extreme, and then eventually back to the door to finish her exercise after 240 seconds. So the displacement time graph's giving us much more information than the distance time graph was. And again, what we've got here is we've got the gradient of the graph giving us useful information. For the first 40 seconds, the gradient is +5, representing the fact that Sam is running in the positive direction along the route. But for the next 60 seconds, her gradient is -5, showing that she's running at -5 meters per second, or 5 meters per second, in the negative direction. The third graph just gives us the speed time graph for Sam's run, and that simply shows that she's running at a constant speed of 5 meters per second according to the model that we've produced. And the fourth graph is our velocity time graph, which shows that for the first 40 seconds, whilst she's moving out to the right along her path, she's moving at 5 meters per second, in other words has a velocity of +5, but for the next 60 seconds she is running to the left, so has a velocity of -5. The next 60 seconds she has a velocity of +5. The next 60 seconds she has a velocity of -5, and the last 20 seconds of the run she's got a velocity of 5. What you might like to think is, how would these graphs change if we had an improved model for Sam's run? So we've seen that the gradient of a distance time graph gives us speed, and the gradient of a displacement time graph gives us the velocity. Now consider a cyclist who's got to ride between 2 sets of traffic lights, and suppose that the graph here is his velocity time graph for that particular journey. Then you should be able to give me a description from the velocity time graph of the cyclist's motion between the 2 sets of lights. So again, just pause the video and write down a brief paragraph describing the cyclist's travel between the 2 sets of lights. So there's the velocity time graph again. The acceleration is a measure of how quickly the cyclist is gaining velocity. And we can calculate that from the acceleration over a period of time is the final velocity minus the initial velocity divided by the size of the time interval. So for the first part of the motion, the acceleration is final velocity 6, take away initial velocity 0, divided by the time interval, which is 4 seconds. So that gives me 1.5 meters per second squared. During the second phase of the motion, well, the initial velocity is 6, the final velocity is 6, and there's a time interval of 23 seconds. So the acceleration during the second phase of the motion is 6 take away 6 divided by 23, so that gives me 0 meters per second squared. And in the third phase of the motion, we've got the acceleration during that third phase of the motion is 0, which is the final velocity, take away the initial velocity, which is 6, divided by the time interval, which is 3, so that gives me -2 meters per second squared. So acceleration is the gradient of a velocity time graph. Now you sometimes need to be able to interpret velocities and accelerations. If the velocity and acceleration are both positive, then the object is moving in the positive direction and is speeding up. If the velocity is positive and the acceleration is negative, then the object's moving in the positive direction but slowing down. If the velocity is negative and the acceleration is positive, then the object is moving in the negative direction but is losing speed, so it's slowing down. And if the velocity and the acceleration are both negative, then the object is moving in this negative direction. The size of the velocity is increasing, i.e. the object is speeding up. Now, before we go any further, we just need to remind ourselves of a result that you'll probably have met at GCSE about the area of a trapezium. So let's suppose we've got a trapezium where the two parallel sides have length A and B, and the two parallel sides are distance h apart. Let's suppose that the area of this trapezium is capital A. And if I produce an exact copy of the trapezium, put it in a different colour, that is also going to have area A. And let's just do a little bit of cutting this second trapezium up. We'll take the rectangular bit up and put it next to the original trapezium. We'll take the we'll take the first of the two triangles, so this is the right hand triangle, and we're going to rotate it by 180 degrees about the right angle to obtain that, and that will then neatly slide in to fill that gap. And we can do very much the same thing with the remaining triangle, which is the triangle at the left hand end. So take it up, rotate it about the right angle by 180 degrees and slide what we've got to join the original trapezium. So what we can see here is that the area of two trapezium make a rectangle whose length is A plus B and whose height is h. So we can say that 2 times A is equal to A plus B times little h. In other words, the area of the trapezium is a half of A plus B times h. So that is a half of the length of the parallel sides added together times by the distance between the two parallel sides. Okay, having established that then, let's go back to our cyclist and we'll think about the distance that he travels. Well, certainly during the second phase of the motion, he is riding at a constant velocity of 6 meters per second for a period of 23 seconds. So his displacement during that period is going to be 6 times 23, which is 138 meters, which of course is the area underneath the graph between t equals 4 and t equals 27. So the total displacement of the cyclist will be the total area underneath the graph. And we've just reminded ourselves the area of a trapezium is a half times the sum of the parallel sides times by the distance between the two parallel sides. So in this case here, the parallel sides have got length 30 and 23. The distance between the parallel sides is 6, so we can say that the displacement is going to be a half of 23 plus 30, that's the two parallel sides, times by 6, that's the gap between the two parallel sides. So that gives me a half of 23 plus 30 times 6, which gives me 159 meters. So the cyclist travels 159 meters in travelling between the two sets of traffic lights. Displacement is the area under a velocity time graph. And a very similar argument gives us that distance travelled is the area underneath a speed time graph. To finish this video then, here are 2 examples, so pause the video and work your way through these 2 examples and take your solutions along to your next lesson so you can discuss them in class. And that concludes then our video on the language and graphs of motion in a line.